Okay, so what we discussed last day is basically we have studied two distributions mainly. One is T distribution, another one is F distribution. And we also discussed a little bit about chi-square because chi-square is one of the ingredients which are one of the random variables which connects normal random variable. Okay, in fact, standard normal. So normal to standard normal, then chi-square. And so yeah, so then we did T distribution, and we also did F distribution, right? F distribution, and these we called uh, sampling distribution, sampling distributions. And why did we call it sampling distribution? Because of the word sampling is coming from the sample. So we have a population here, and we want to study some properties of this whole objects in the population, all the objects in the population, but we cannot do that. So in general, intensity, because it is less large, or maybe due to some other issues, some of them are not exactly known or something like that. So we want to pick a small amount of that, which we assume to be 5% of that, which is called as random sample. So this sample, random sample, contains, let's say, endpoints. Then there is a population random variable, that is x, and then we have x1, x2, this this random variables corresponding to the n random samples, and these are all IIDs, and they have the same distribution as x. And then you said, what is something called a statistic? Statistic is nothing but a function. Okay, we denote it as a t. This is a function of x1, x2, dot xn. And then we said, okay, the distribution of this statistic is called a sampling distribution. Okay, I mean, whatever statistic you consider doesn't matter. Okay, that will have, again, so this is basically a random variable. This statistic is a random variable, so it must have a distribution, and that distribution is called a sampling distribution. And we have seen that if we take very specific kind of functions, then the distribution of those statistics, okay, are chi-square, T distribution, or F distribution. These are the primary like sampling distributions which we talked about. And now today what we'll do, see, our original goal was to say something about the population from the sample, from the random sample. Okay. Now, and we also said how we are getting this population, because we are measuring something, okay, corresponding to some experiment. We are measuring something. Now, we do not know, let's say, the PDF, okay, or the distribution function of x. Let us assume that it is called the PDF. I mean, it is denoted as, let's say, x and theta. Okay, theta is a set of parameters, okay, or theta can be, I mean, one parameter is theta, but if I write it as a bold, theta bar, theta, something like that, in many books, people use many notations, so you can have more than one parameters. For example, suppose I know that the population distribution, okay, the density function corresponding to the random variable x is normal, but I do not know what are mu and sigma square. Unless I know mu and sigma square, I do not know exactly the PDF is, okay? So the thing is, these are the parameters, okay, in bold to define the population distribution, okay? So the idea is then, from the knowledge, I mean, I can acquire the knowledge about this distribution. Suppose somehow I know that it is normal. Somehow I know it is exponential. I know something about this PDF, okay? But I exactly don't know about the values of these parameters, okay? So I have some knowledge about the PDF, and I want to gain some more knowledge about the population, meaning about this parameter theta bar or theta from the sampling, from the random sample that I have. So now the goal is, now we are changing our goal a little bit. Earlier we are interested about knowing, let's say, population mean, population variance. And we have discussed all these things. Now we are saying that suppose if it is also assumed, or suppose I know the PDF, but we do not know the parameters involved to define the PDF, then how to estimate the parameters from a random sample. Okay? So the goal here is now, given the PDF, when I'm saying given the PDF, that means I have the knowledge about the PDF, but this theta is not known. Okay, in bracket let me write theta is not known. That means the value of the parameters are not known. But if theta is only one parameter, is or are not known. Okay, so given the PDF, okay, we want to gain more knowledge or more information, or something called statistical, or let me write for the timing information about f, or let's say f of x. Okay, f of x, using the sample, let's say x1, x2, xn, whatever the sample are. So now, once we pick this sample, okay, so that is not a random variable anymore, because I mean, for the example of our battery, lithium battery, we're talking about lifespan. So if we choose, let's say 10 batteries, and if we observe its lifespan, we get 10 values. If we choose 10 random samples, means random batteries, then we'll get, if you observe the lifespan, then we'll get 10 numbers. They are not random variables. They are the values associated with the random variable. So I'll get this kind. So random sampling here now, after doing the random sample or random sampling, okay, what we get is x1 is equal to some small x1, x2 is equal to some small x2. Of course, as I said before, this small value, small x1, x2, xn, that depends on the choice of the batteries, choice of the objects which are in the sample. Okay, depending on the sample, what about the objects I choose, depending on that, I'll get some values. x1, x2, xn, small x1, small x2, small xn. And this is called sample data. This is called in general the sample data. Okay. Now, our idea is to employ any statistical method or the knowledge of statistics. I mean, basically the idea of statistics is about developing methods, okay, to gain information about the population from the information about the random sample. Okay. Now here, if I assume that the density function of the population is fx theta, and I do not know the value of theta, then one of the goals is to estimate the value of theta. Then the second question could be whether that is a good estimate or bad estimate, right? Or maybe whether this distribution is at all a correct distribution or not. This could be the part of my statistical inferences about the population. So what do we mean? So there is a course actually called Statistical Inference, okay? So that is also offered from Maths department. I think next semester also this course will run. Statistical inference. So what is the subject of statistical inference? NCE, okay. Okay, so the object of this, what is this statistical inference? So I have this random sample. Now using this random sample, I can have three things. One is something called estimation. Estimation is to deal with estimating the values of the parameters. Meaning here parameter theta, let's say. Parameters or tar, whatever is theta. Only one theta or many thetas. This could be one object or one goal. Another goal could be hypothesis testing. Okay, so here when I say estimation, see, I said, okay, suppose we estimate some value of this theta, then I also have to judge whether that estimate is a good estimate or bad estimate. Okay, so that's a part of estimation itself. Now, if I say hypothesis testing, okay, so in a broad sense, hypothesis testing is related to understanding whether my hypothesis about the PDF, that means if I assume that the PDF is normal, let's say I assume that this is normal, if that hypothesis is true or not, if it is true, how much true it is, I have to test that. So this is about hypothesis of the distribution of the population. Okay, we'll also talk about that maybe next week. So this is what is called hypothesis testing, and another, in the bigger sense, is called prediction, which we'll not do in this course. So mainly we'll talk about these two parts of statistical inference, which is estimation and statistical inference. Okay. Now, see let me just because this is important. Okay. So we started with the population. Then, in order to understand the population, what we assume? We assume that suppose we know that density function need not be known, but if it is known, let's say, if somehow we can guess that this is normal, the way it is produced, or this is Poisson, the way it is produced, and so on. Okay, from the mechanism, from the procedure, from the technology, how this data set is obtained. Okay. For example, I mean, it could be like, I mean, I can give you a practical example. Let's say, you see, whenever you watch YouTube videos, okay, they always give ads, a different kind of ads. Now, if during the ad, if you click on that video, in most of the cases, that will directly take you to an web page regarding that company which is giving the advertisement. Okay. Now, suppose you want to do a statistical study. Suppose there is a company, okay, which gives you a job, and the job is to study whether people are clicking on that ad which is shown during a video or not. One thing could be, okay, for the company is to decide what kind of ads should be displayed during a video. Now, video could be related to a politician, could be a politics, it could be related to some cooking, could be some entertainment video, whatever it is. So depending on the context, the company has to first decide which ad to be displayed. And what is the purpose of this company? The company wants to make profit. Okay. So company wants to reach to a higher number of customers or consumers. So they want to basically turn this consumers into customers, right? So that is their goal. Okay. Anyway, so I'm saying just a practical problem, because these are all important. Okay, but it does not mean that this is politically correct. Okay, so I'm not talking about politics here. Whether it is a good thing or bad thing, I am not deciding that. Okay, so apart from all this, what I'm saying is this is a statistical problem. Now, suppose the company employer give you the job, decide which ad should be displayed during a video so that many people click on the ad. Okay. Now, if you just observe, okay, when you are watching videos or your friends or family members are watching videos, YouTube videos, let's say, and you see an ad, how many times do you click the ad? Okay. How many times do you click that? You actually, it's not very frequently, maybe one time, once in 100, let's say. Okay. So most of the cases you skip the ad. Okay. Now the question is then how to decide if this is the pattern of the consumers, okay, or this is a pattern of the customers, whatever it is. So then the question will be how to decide which kind of ads, advertisements should be played during which kind of videos. Okay, and I'll try to observe the pattern of the consumers who are watching the videos. So this is a totally statistical problem, okay, because there are a lot of uncertain parameters involved here. There cannot be any deterministic model which can model the situation. So probably there is a big data the company has, let's say, I mean the company you're working for, let's say, they have like a big data, and the data talks about these are the ads, okay, these are the videos, when it is played, okay, how many are clicked, and so on. And then you see that the number of clicks, okay, is very rare. It is a rare event, kind of an event. Okay, it's not very frequent. Okay, so then the idea is so what is the distribution? Like out of 1,000, how many times people are saying, okay, so what is the favorable event? What is not favorable, and this and that. So this is completely a realistic problem which is hard to solve. First of all, the data is given to you to be very huge data. let's say 1 crore people, let's say 100 lakh of people, okay, are watching the videos, because YouTube videos many people watch, okay. It could, I mean, 100 lakhs could be small number, okay. Now from that statistic, how do you sample in order to understand the behavior of the people? That's the first job. And somehow if you are able to make a random sample out of it, then your idea will be, what is the distribution of the population? What is the behavior of the population when it is clicking, when the people are clicking on the ad? It's typically a problem, practical problem, where this kind of situation will come. Suppose you assume that it is very rare event, kind of a, let's say, Poisson distribution. Then Poisson distribution, there is a parameter, average number of, let's say, whatever the parameter lambda is. Now you have to estimate the value of that lambda. So this is, I'm just telling you, because this occurs very frequently in practical life. When you work for a company, let's say you are working for some company, okay, and they want to solve some problem using your intelligence or using your knowledge in statistics and computing, let's say, okay. So this is a very serious and this is very important thing. So then the question is how to estimate this theta, okay. Now before I estimate this theta, okay, so there is a function, or there is a PDF which I already know, but I do not know the parameters involved to define the PDF. Then what I have to do is first have to find what is the feasible set of this parameter theta. So that is what is called parameter space. Parameter space is very simple concept. So parameter space, I mean, what are the values of the parameter could take? This is known as parameter space. So parameter space, so let's say to define it, let's say suppose X is a population, X is a population, okay, with PDF. This is your assumption with PDF fx. I'll just not denote fx as okay, whatever it is. So yeah, and theta is unknown. Theta is unknown. Okay. Now parameter space, I'll write this as omega. This is all those theta. Let's say there are m number of parameters. So they are, let's say, real parameters, such that f of this x theta, I mean, this function is a PDF. So these are admissible values of these parameters. That is what is called the parameter space. For example, I mean, if this x is, let's say, exponential, so there is one parameter in the exponential. Okay. Now what is the parameter space? So then the answer would be, I mean, if you look back, that is the PDF. Okay, the PDF was what? F theta or fx theta was, I think, 1 by theta to the power minus x by theta. So first of all, theta cannot be 0, and theta also has to be positive, otherwise it will not be a density function. So this is theta, all this, okay, such that 0 less than theta less than infinity. So I can just say it is 0 to infinity. This is the parameter space for exponential. Okay. Another question could be, I mean, another example could be, let's say x is normal, mu sigma square. So what is the parameter space? So your parameter space is all this theta belongs to R square now, okay, such that fx theta would be normal. And here sigma square cannot be, let's say, negative number, because it is always positive, the variance, okay. So this is the set of sigma mu square, which is in R square, such that mu could be anything, okay, but sigma could be bigger, should be bigger than 0. So here this is like R means mu is varying on R, and this is R plus. Okay, if I denote this as R plus, okay, R plus. So this is basically then what? This is the entire plane here. This is the entire plane here, the upper plane of this. Okay, the entire plane here. So the upper plane. So this is the parameter space. So given any plane, so given any assumption on the density function, first of all, you have to decide what is the parameter space, because from that parameter space only you have to find a theta. Okay. Now, why I'm focusing on this? It is very simple, but why I'm focusing on this? Because somehow I need to probably optimize. Okay, I have to. Okay, we'll see it later. Okay, but there is some importance about this space. Okay, so I have to basically optimize the function. The region is this. Okay, based on this thing, I have to optimize it. Okay, so in general, what we'll assume, for our study, we'll assume that the sigma sorry, this omega is a subset of r to the power m. That means there are m number of parameters. Okay, whatever, this is a subset of this. Okay, now what I want to do, the problem is estimate theta. So theta is a vector here. It can be theta 1, theta 2, dot, 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 theta m. There are m parameters involved. Okay, how I am going to estimate this? Estimate this from the sample. Suppose I have n sample point. Okay, and now recall when you define statistic is actually a function of this x1, x2, xn, and that statistic does not include the parameter involved to define the density. So it is independent. The statistic is independent of any statistic is independent of the parameter involved for the distribution. Okay, so in general, it is just a function of x1, x2, xn. So you can watch the video. It's the lectures video that I said it iteratively that statistics should be independent of the parameter. It should be just purely a function of this. Now I will define what is called an estimator and what is called an estimate. Okay, so this is my definition of estimator. So I have to estimate theta, the parameter or the parameters, okay, using the random sample. Okay, so let me set my notation here. This is, let's say, f x theta. Okay, and let's say the sample is x1, x2, dot, 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 xn. Okay, which are all IID from x. So this is a random sample. Now I'll say an estimator is a statistic. Okay, that can be used to guess theta. This is the definition of estimator. Estimator is what? So I get the sample data, let's say x1, x2, xn using the random sample, whatever the sample is. So that's why I'm writing it as a random variable. But if I choose the sample, then it becomes a set of numbers only, small x and small x. Now using these numbers, okay, I have to define some function, something I have to do, some algebraic manipulation to guess the value of theta. Okay, and the value which I guess, okay, that means the numerical value corresponding to that statistic is called the estimate. And the numerical value that I guess for theta, okay, is called the estimate. Okay, and for this estimator, see, estimator is a statistic. For what? The statistic to guess theta. So I have to introduce a notation for the estimator for the parameter theta. So I'll denote the estimator as theta hat. So by this, what I mean is, suppose that fx x theta is nothing but normal, but I do not know mu and do not know sigma square. Then I have to first find a statistic using the random sample x1, x2, xn. Okay, such that will estimate mu, and another statistic that will estimate sigma square. So basically, find in the notation, I'll just write find mu hat and sigma square hat. So what is the estimator for mu? What is the estimator for sigma square? And what are your estimates? Okay, this is the question. Now, there are several methods to do it. Okay, for example, there is one called moment method. Another one is called maximum likelihood method. Likelihood method. Bayes method. Then least square method. There are many methods. Okay, least squares method. Minimum chi-square method. Chi-square will also again play a big role when I will talk about testing of hypothesis. Minimum chi-square. That's why I said the what is called the degree of freedom of chi-square. Okay, and we also have seen that the random, the sample mean and sample, let's say, variance. Okay, they have different kinds of degrees of freedom. In fact, one is n and one is n minus 1, depending on if the random sample is R or let's say standard normal. Okay, we proved this last day. So chi-square will play a big role, and we'll talk about the degrees of freedom. What is the role it is playing? Okay, I'll say a few words about degree of distribution. What is the meaning of that? But minimum chi-square method, and so on. And there are other methods also. But in this course, I just talk about briefly about moment method and maximum likelihood method. There are other methods as well. Okay, this is not the end of it. So there are different ways to estimate the value of the parameters. Okay, now let us first talk about moment method.
Sir.
Yes.
Sir, we can directly find the mu and sigma square as we have the x1, x2, and x3. No.
Yeah, we can. I mean, how do you find that?
Sir, we have the values like x1, x2, and x3.
Yes.
So
yeah.
We will then we directly just calculate their mean.
Yeah, we can. But how do you know that will estimate mu? Let's say you are talking about 100 numbers. Suppose you know normal that also. Now I said 5% is the random sample. Now I give you 5 values, arbitrary 5 values. Okay, and you just calculate their average. Means average there. But how do you know that will estimate mu? So if I just arbitrary, so random sample is arbitrary, right? So if I pick any numbers, okay, suppose I give you 1 to up to 100, 1, 2, 3, 4, all the integers. That is my sample. That is my population. Now I give you any 5. Let's say my choice is 5, 70, 35, 80, 50, something like that. And you take the average of this, you get a value. Then the question is, I mean, if I take 1 to up to 100, that will not be following normal, but I'm just saying, okay, because if you have any distribution, it does not mean that the mean of the distribution is exactly the mean of the sample data. Instead of this n mu sigma, it could be some arbitrary distribution as well. But if I just give you this random sample data, if you take the mean of that need not be the mean of the corresponding distribution, because distribution could be anything. Here I am assuming it is normal, let us say. This is just for the sake of example I'm saying. But it could be anything, f x theta. And suppose you want to estimate the mean of the distribution. You just cannot say that I have this random sample, let's say 5 values. If I take the mean, that will estimate the mean of the population distribution. That cannot be the case because it is valid for then any distribution. It cannot be true, right? You understand what I'm trying to tell you?
Yes, sir. Yes, sir.
Okay. So that's why we need what? We need some theoretical. We need to do some theoretical study. That is the importance of these theorems. If it is normal, then the question will be X bar, the one you are talking about. Is that a good estimator, or is that at all? This is a statistic. Is okay? Does it? I mean, is it an estimator for mu? First question. I have to prove that for normal at least. If I give you, let's say, exponential, then I have to again ask the same question. Is this, or let's say, uniform distribution? Because uniform and normal I'll do. Okay, for uniform also, is it an estimator for mu? Now I am saying estimator, okay, but I do not know how to check whether it is an estimator or not. Some statistic is an estimator or not. Instead of x bar, I could have said x1 square plus x, so sum of xi square. Is it an estimator for mu? I do not know. So my estimator has to be decided based on something. And something is the method. Which method you choose to show what is the estimator? What is the estimator means? If I give you a statistic, some function of this x1, x2, xn, then you need to check and tell me whether that statistic, that function, okay, is an estimator for the parameter. Let's say here mu. Okay, so I need to check that. So here is one method to estimate to decide whether it is an estimator or not. Okay, and then once I decide on the estimator, then I can find the value. I can put the numerical value because I'll just place, once I decide the statistic, then this is a function of x1, capital X1, capital X2, capital Xn, and I have the sample data, capital X1, I'll replace that by small x1, capital X2 will be replaced by small x2, and dot 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 capital Xn will be replaced by small xn, and then I have the value, and that will be the estimate of the corresponding parameter. So here is the method. Okay, so there is a philosophy about this method. I'll talk about that later. But first, let me define what is this method is talking about. Okay, so it is saying that if x1, x2, xn, okay, if this is the random sample from x, okay, then there is something called, which I said, the density function of the sample. Okay, so you can say f of x, theta 1, theta 2, dot 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 theta m. Suppose there are m parameters. We are doing it in general. Then I can talk about moments about the mean, central moment, x to the power k. What is that? This is nothing but minus infinity to infinity, x to the power k, and this x theta, or let's say theta 1, theta 2, theta m, whatever. So here theta is replaced by theta 1, theta 2, theta m. I have to emphasize that there can be multiple parameters. Okay, then dx. This is the kth population moment. And same thing I can do for sampled data. So for the random sample, I can also define the moment. Let's say mk is 1 by n sum over xi to the power k, I equal to 1 to n. So I have k, n values. Okay, if I take, let's say here any k equal to 1, so it is nothing but expectation or the average value. If I take k equal to 2, that's a second order moment, a second moment. 3. So I have these discrete values x1, x2, xn. Okay, I can take the average of this, sum of this. So this will be my first. Second is what? I'll take the square of this by n. Third moment is cube this by n, and so on. So this is my central moment function for the sample. So I'll call it the kth sample moment. And I have this kth population moment. And the method says, whatever be the value of those parameters, okay, I want to choose those values based on the fact that these two moments are equal. Okay? So this is the method. Okay, so find the estimator. Here I'm finding, this is the method. Find the estimator for the parameters theta 1, theta 2, theta m by equating the first m. So here it is important. M is the number of parameters, and m population moments we are considering. Population moments. Okay, if it exists, of course. If the moment does not exist, then this method will not work. Okay, if it exists. If exist. Okay, to the first m sample moments. I'll equate it, and then I'll solve some system of equations, and then sample moments, and then that will give me the estimator. So that is what I'm saying. Expectation of x should be, so this is a theoretical thing. So this is given to me, this function x, f is given to me, okay, using the parameter theta is. So I can calculate ex. So I want this to be equal to m1, this value. This is a number, scalar, based on small x1, small x2, small xn. Then I can say it is x square is equal to m2. I'll keep on doing this up to mth because there are m. I want to have m equations to solve because I have m parameters to solve. So I want to solve this system. Okay, and this method is known as the moment method. And this is one of the classical methods for estimating the parameters. And this method is developed by Carl Pearson. He's also a British statistician. Carl Pearson. This was in 1902. Okay. Now I will see, using this method, what are the estimates for normal, let's say. So estimates for parameters involved in normal. So the first example, first problem, or you can say example. Suppose x is this, n mu sigma square, and I have the sample x1, x2, xn. N sample I have. I have to estimate. Estimates I have to find the estimators. I have to find the statistics, which will estimate mu and sigma square. Estimate mu and sigma square. For a practical problem, we have these values, but I'm doing it theoretically, meaning these are random variables. Now I have to find some function of this x1, x2, xn, some statistic, which will estimate mu using this method. Okay. So what is the answer? What is the solution? Okay, Ex is what? I know that it is normal, so Ex is mu. Okay, and Ex square is what? It is mu square plus sigma square. Okay, you can calculate and check. And then due to the using the method, using the momentum method MOM, okay, using MOM, mu should be equal to X. I want this to be equal to M1, but M1 is what? M1 is 1 by n sum of xi's I equal to 1 to n. So this is my x bar. So x bar is the estimator for mu. So I'll write mu hat is equal to x bar. See, if it is not normal, this need not be true. This calculation need not be true. Okay. But use for the normal case, at least we have this. Now we'll find, let's say, because why I'm saying is because this parameter itself is the mean. But you have distributions where parameters are not the expected values. So you have to calculate their expected values and then you have to equate it with M1. Here parameter itself is the mean. But in many distributions which you talked about, the parameter is not exactly the mean. Okay, you have different values for the parameter, for the mean. Okay, now for sigma square, we'll do sigma square. For sigma square, we're going to find an estimator. So sigma square, I'll give you an example quickly. So I can write it this way because I know how to find it. So it has to be this minus mu square. I mean, it is equal to this because of the definition of sigma square. I could have just written this. Now I want e to the power x square should be equal to m2. That was my goal. So I want to use this fact, m2. Here I use this fact. Here I use the fact that to estimate mu, I use the fact Ex equal to M1. Now, in order to estimate sigma square, I am using Ex square is equal to M2. Okay, and Es square is equal to M2 means this is M2 mu square. But M2 is what? This is 1 by n sum over xi square minus this is x bar square for my sample. So this is, I mean, this is how I'm writing it, but you can do some algebra and can prove that this is exactly equal to this. But the calculation is long, so I'm not showing it to you. So basically what is happening here is this sample variance, not exactly the sample variance, because for the sample, okay, let me just write it. So sigma square hat, this is the estimator for this, is 1 by n sum over I equal to 1 to n xi minus x bar square whole square. This is the estimator for sigma square, but this is not a square. This is not a square because for a square you have n minus 1. Here I have 1 by n, not 1 by n minus 1. So for sigma square, for the second parameter for normal, this is the estimator. Okay, which is this function. This is the estimator. And this is the estimator. The sample mean is itself the estimator for the mean. Okay, now let's see another example quickly. Another example, let's say here, I'm just writing fx theta. I'm just writing the PDF, which is, let's say, theta x to the power theta minus 1 if 0 less than x less than 1 and 0. Yes?
Sir, can you just show just previous year?
Huh?
Above this, before this, sir.
Yes.
Yes, sir. Yes, sir. Yes, sir.
Okay.
Here, sir, you have written sigma square plus mu square equals to e of x square. Sigma square equals to, you write sigma square plus mu square minus mu square. Then you
Yes,
write the
yes,
sigma.
yes.
That I don't get,
Yeah.
sir. Sigma square plus mu square is equals to e of x square.
Yeah, you can calculate this. You can forget about this line. It is by definition, it is this. Okay. You can show that it is the case that if you calculate ex square, that will be sigma square plus mu square for the case of normal. Okay.
Yes.
You can start from here, not a problem.
Yeah. Yes, sir.
Okay. 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 Another example here is this. Okay. Now here there is only one parameter, so I just have to use using MAM in order to find the estimator for theta. What I have to do, I have to equate this with M1, right? Now, so then I have to first find what is this one. So if I find this Ex, then what do I get? It is only non-zero when it is 0 to 1. So I'm just finding X, Fx. Fx is theta x to the power theta minus 1 dx, which is what? This is theta will come out 0 to 1 x to the power theta dx. So this is what? Theta by theta plus 1. Theta is the constant here, theta plus 1 and x to the power theta plus 1, right? 0 to 1. So it is basically theta by theta plus 1. So this is the expected value of this expectation of this random variable. So I have to equate this using MOM. Using moment method, I have to do theta by theta plus 1 is equal to x bar, because this is what is M1. So then what is theta? So theta is, I can directly write x bar by 1 minus x bar. So therefore, what is my theta hat? Theta hat is my x bar by 1 minus x bar. This is my estimate. Okay. Now see here, if we get x bar, means if you have some sample value, sample data, you can find its corresponding value by putting x bar equal to 1 by n sum of xi's. You'll get some value, and that will be the numerical value. That will be the estimate for theta, a numerical value. Okay. I can give you an example. For example, for example, suppose n equal to something. Suppose n equal to some 4. Okay. And suppose we get the sample value is something 0.2, x3 is equal to 0.6, x3 is equal to something 0.5, x4 equal to 0.3. Then what you do is you first find out the estimate for theta, which will be x. If I have to first find x bar will be what? This plus this plus this plus this. 6, 9, 9, 10, 11, 16. Okay, 16 by 4, so 0.4. Then what is the estimate? Estimate will be 0.4 by 1 minus 0.4. So which is what? Which is 2 by 3. 2 by 3. Okay, this is the estimate for this using the sample. See, I do not know anything about theta, but if you give me a sample data, let's say this is my sample data. Okay, from here I can estimate my theta. Okay, which is this. Another example. Now, what is the basic principle here? So this is the principle. I said I will discuss this later, but let me just write it down here. Principle, I am running out of time. Principle here is decide the unknown, the value, decide the value of the unknown population parameter, okay? The sample data, or you can say observed data, and better word is sample data, okay, have the same moments as the population. This is the basic principle based on which this method is standing. Okay, and the most important example. Okay, most important example is this one, because I mean why it is important. I'll say this later. But let me just see. So this is the uniform distribution around, let's say, 0 less than x less than theta. Okay, and 0 otherwise. So 0 to theta, it is 1 by theta, and otherwise it is 0. Okay. Now, what is the estimator? Can anybody tell me? What is the estimator for this theta here? What is E of x? What is E of x? Directly, I can write it down. So x here is basically uniform. Okay. 0 to theta. Ex is only what? Expected value of x? 0
1.
to theta. Bolo.
1.
1. So expected value will be what? X fx dx, right? But this is from 0 to theta. So how do you get it?
Theta by
2. Yeah, we did it before. Theta by 2. Now theta by 2 has to be equal to m1, which is x bar. Then what is theta? Theta is equal to 2 times x bar. Therefore, theta hat is equal to 2 times x bar. This is the estimator. 2 times x bar is the estimator for theta. So remember this. I'll show you some interesting fact about this. Means the question is now, and now so this is my enough example. Now I'll say a different method. Now the question is, so the most important question is, I have different methods, and each method will give me an estimator for the same parameter. Here the method is what? I have to equate the moments. Let's say m number of moments, if number of parameters is m. Solving that, I will estimate. Using some other method, which I'm going to talk next, in some other method, I'll be able to find another estimator. But that estimators could be different. Okay, and I'll show that this will be different in this case. For example, I'll give this because this example is small. I'll give this example. I'll talk about another method. I'll show you that it could be different. And if this could be different, then another question comes. If you have different estimators for different methods, which one is the good estimator, which one is the bad estimator? So this is interesting now. So, okay, let me talk about another method, which is, I mean, I don't have much time, but let me just, let's say, maximum likelihood method. Okay. So this method was first used by Fisher again, Ronald Fisher, and it was around 1922. Okay, but I mean, people say that according to the history that this method was earlier also introduced by Gauss and Bernoulli. Okay, but anyway, so let's just say that we have this in 1922. So what is the definition here? Here, what is the principle? What is the mechanism here using this method? Here, they are using first, they are defining a function which is called likelihood function. Okay, this is the first thing we have to know. Likelihood function. What is this likelihood function? So it is saying that if we have the sample x1, x2, and xn, okay, and each is IID, so random sample is IID for x, and suppose this fx theta, okay, is the PDF, and theta is unknown. Then I define my likelihood function L theta is just the product of f xi theta, I equal to 1 to n. So I have n samples, so make a product of this, and then I have this thing, likelihood function. Now, so what is the likelihood function basically? So it is basically the joint density function, you can say, that is the joint, which I talked about it before, joint density function. Why it is product? Because they are independent. Joint density function for the sample, okay, for the random sample, or you can say random variable x1, x2. Now, the mechanism here is, the principle here is, the estimator is that value of theta which will give me the maximum value of this L theta. Okay. So that's why it is called maximum likelihood estimator. Okay. The maximum likelihood estimator is that value of theta, which will basically give me the maximum value of the joint density of the random sample. Maximum, that is the value of theta which gives or which maximizes L theta, the likelihood function. So in notation, we'll write theta hat is argmax. Arg means argument. I'll tell you what is this. So this is a new notation probably for you. Earlier you have seen without this argument. Okay, you have seen maximum of some theta. Here the same thing, but when I write arg means the argument, meaning this theta. So this is the value of theta. It is not the value of this function. No, that is the maximum value of L theta, but it is not. Theta hat is the theta which maximizes this, and this is the notation. When you write arg, argument maximum this, it means the theta here, the argument which maximizes this function. That's why the argument was used here before this function maximum. So if you just forget about argument, it will give you the maximum value of L theta. But when you write argmax, it means the argument which gives the max. And that is what is called theta hat. Okay. I think I don't have any more time. So yeah, maybe we'll talk about this next week. Yeah, so here are many things. I mean, let me just say it. So this is the remark. I mean, I do not know how much I'll be able to discuss, but let me just say that different methods, okay, will produce different estimators, and it could be a good homework to find out the estimators for uniform distribution, for estimators, and for this theta, estimator for theta using maximum likelihood function or maximum likelihood estimator. Or if you have normal, okay, you want to estimate mu and sigma square using the maximum likelihood estimator, then what are those? Are they really x bar and this function or not? Okay, that could be a good question to begin. So we'll produce different estimators. Then, I mean, this need not be, may produce the same also. So different methods may produce, not will, but may produce different estimators. Then the question is, which one is good or which one is bad? This is the first remark. Second remark is, using this method, I'm pinpointing a value to estimate. Meaning, let's say my population mean, okay, is, let's say, 5. Now I want to give you an estimate for 5. So these methods are actually the part of called point estimation. Meaning, I want to approximate the value of 5. But can there exist a concept, or does there exist a concept to estimate this by an interval, not pinpointing the value? And there exist such methods, and it is called interval estimation. We'll also talk about that. And then comes about our assumption. The assumption is that I know the density function. Okay. But the question is, that is also hypothesis. I'm assuming that this hypothesis is correct, that this is the true density. Then the question will be, is that hypothesis is true or untrue, right or wrong? Okay, if we get time, we'll discuss that as well. Yeah, here I stop. If you have any questions, you may please ask.